Welcome everyone, and today we are going to be talking about bivariate correlations, understanding and confusion all at once, right? So this is chapter 3 of your book. By bivariate, we means we are looking at two data sets or two data simultaneously, two variables simultaneously. So what is correlation? Correlation is to show that how the two sets are related to each other. So if you look at your book on page number 45, you have time spent exercising and the weight loss. If you spend more time exercising, the weight loss would be more. Or if you spend less time, the weight loss would be less. Basically, it shows a relationship between two sets and how strong or weak is the relationship. That is what is the correlation about. Correlation only is showing you how these two pieces of information are related to each other, but they do not show a cause-effect relationship. Even though we say that more time spent exercising relates to more weight loss, we cannot say that that is what causes the weight loss. It could be other factors also. So you have to remember this is the fact that it does not indicate a cause and effect relationship. This is very important. And we are going to bring this back again. But one of the things that I had said in chapter 2 was us to look at the types of data again. So this is my types of data, the ordinal, the Roscoe, the nominal, and the dichotomous. This slide is exactly the same as the slide in chapter 2, but what I did was I took each one of them and have expanded that. So let's look at the ordinal data. When you look at ordinal data, it is a rank order. So when you are talking about, let's say, the letter grades, A, B, and C, it is in rank because if you have a 90 and 100, yes, you have an A. So that is an ordinal data. You're looking at Likert scale is when you say is strongly agree, disagree, neutral, or strongly agree, whichever range you do, but those are ranks. Class ranks are all ordinal data. Like here I have hot, hotter, hottest. So if I give them values, this is an ordinal data. It occurs in order. Nominal data is each of them has a value and they are mutually exclusive. There is no logical order in it. Like gender, male, female, there is no logical order for it. Ethnicity, race. We talk about groups. We talk about hair color. We talk about, we can talk about, like if you're talking about blonde, black hair, brown hair, there is no logical order. They are mutually exclusive quantities. Nominal is you give them a number. It is, and I'll explain why types of data is so important. So interval is which occurs in specific order and it reflects equal differences, like your GRE scores, your IQ scores. This is my IQ. So you know what is the IQ. There are equal differences between each point. That is an interval data. And then the ratio data is the data that has a true zero, which means like income. Income can be zero, and then weight, height. In real life, you obviously cannot have a weight of a zero, but that is what is the fact is between the ratio and the interval is the ratio has, it also reflects equal differences in its logical orders, but it could have a true zero, which is not possible in the interval data. So why have been talking about all these different types of data? We have been talking about the types of data because it is the only the interval and the ratio data is where you can do the mathematical operations. Like we talked about in the chapter 2 is the mean, median, mode. And now again, when we will talk about if further go ahead is the t-test and all those things. So mathematical operations can only happen on interval and ratio data. We can do correlations on the nominal and the ordinal data, and there are techniques for it, but most research always, whenever they talk about correlation, they talk about Pearson correlation, which is on the internal and the ratio data. The dichotomous is basically nominal data that has only two values, yes or no, male, female, that type. So let's go further and look at the correlation research. So once again, it explores the relationship between the two variables. So two variables as opposed to one indicates bivariate. Now your relationship could be high, which means more I exercise, more weight I lose. So they are both high and high. It could be low and low. Less I study, less grade I get. So low and low. It could also be a high and a low relationship, and a low and a high relationship. These relationships are given on page 45 of your book if you want to read more, and we are going to talk about all of these types of correlations. So correlation coefficient gives you the strength and the direction of direction of a relationship. Now, as we talked about, there is much more probability of having a high and a low relationship than a high-low and a low-high relationship. That is very little systematic tendency that is there. So let's talk. So when you're looking at a coefficient, the correlation coefficient, when they give you a correlation coefficient, which is most commonly the Pearson product moment correlation coefficient, it is between -1 to +1, which basically means that a -1 is they could have the most strong correlation, but it is negative. And then a positive is when it has the most positive relationship. So negative would be low, and positive is high and high. If you look at page number 49 of your book, it is going to show you that a direct relationship is a positive relationship, and an indirect relationship is an inverse relationship, which shows a negative correlation. The term high is used when the correlation coefficient is closer to -1 or +1. So it's closer to the two ends. And a weak relationship is when it is closer to 0. I have a diagram here to show you guys. So if you look at this one, -1 to +1, you have a -0.8, a 0, and a 0.8. So if you have, there is no correlation between money and weight, but height and longevity has a 0.8, which is a strong correlation. Smoking and happiness has more the smoking, less is the happiness. So this is where, do you see where the high and the low is coming in? More smoking is less happiness. Let me correct this once again. Positive is high, low, and then you have your negative to be high, low, high. So this is what it is. Sometimes researchers try to say that a 0.5 is a very moderate or close to strong relationship. So they try to do that based on their own discretion, but basically 0.6 and above, 0.6 to 0.8 is moderate, 0.8 and above is more stronger correlation, and 0 to 0.5, 0.6 is generally weak. correlation, and that is what is there for the other end also. 0 to negative 0.6 is like weak. Those labels are reported, as I said, at the discretion of the researcher, but because they have the values, that is what lets the readers decide whether it is true or not. So if I go back and you're going to look, here is some examples of it. High school class rank and college success, SAT scores and college success, height and weight. These are those things. As you are looking for your research topic, think about your variables. Is it a single variable? Is it a bivariate variable? What kind of a data set is that? So here is one of my data set which has an experience in years and then income in the thousand. This is just the subject number. So if I look at this data set, what kind of information is included? I have the experience in years is given, income in thousand is given. I can also see, does it come from a range of number or does it appear to be yes and no? So here is where you're looking at, is it a nominal data or is it an ordinal data? What kind of data it is? This is not a nominal data. This is not an ordinal data. You have is what is called the ratio data here so that I can do mathematical operations on it. How many comparison can we make? This is an important question. It is there in your assignment also. If it is having two variables, like I have the income and the years of experience, I will use this formula to find out how many correlations can I do. So two variables is 2 minus 1 divided by 2, which is 1. So in this data set, I could only make one correlation. But if I have 3 data set, then it will be 3 minus 1 divided by 2, which would come out to be that I can make more than one correlations. So variables, number of variables determine how many correlations can you make. So now I've taken this data and I've actually used to make scatter plots with it. Scatter plots provide you immense amount of information about the data set. The scatter plots, if you look at it, has two things. You have your horizontal axis and you have your y-axis. So your horizontal axis is your years of experience, which is the abscissa, and then the y-axis is your income, which is the ordinate. Page number 46 has this. Basically, the scatter plots provide you the relation or reveal the relationship between the two variables through the pattern formed by the dots. So if you look at the dots, they are going, they are in the increasing order and they mostly lie on a straight line. They don't have to perfectly align on a straight line, but if I draw a line of best fit, I would see some are above, some are below. So basically they are making a positive correlation and they are going in the straight line. This is very important for you to understand, is because there are different types of correlations. Let me show you that slide. So we were looking at these different types of correlation. So if you look at this correlation, what you are noticing is the fact that it is a positive one correlation, which means when your x is increasing, your y is increasing. So it is a positive one. And it is a very strong correlation because the maximum value a correlation coefficient can have is a positive 1. If you look at this one, is you are seeing is when your x is increasing, your y is decreasing. So this is where the high low and the low high comes in. Is x is increasing, your y is decreasing, and it's a negative 1 correlation, but it is a very high correlation because the maximum value on the left hand side that a coefficient correlation can have is a -1. 0.6 is a moderate correlation, but this is a positive correlation because when X is increasing, Y is increasing. But here again, when X is increasing, Y is decreasing. Scatter plots are very important, and research actually recommends for you to do actually scatter plots to look at the spread of your data before you do any statistics on it. And we will talk about outliers and other things also. The research that gets accepted does do the scatter plots, and then they work on the other statistics. Here you can see the spread is all around. There is no defined spread, so it is a it is a zero. The correlation coefficient is zero. R is, if I have not said this before, R is your representation or symbol for correlation coefficient. So what are the scatter plots? They are a visual representation of a data. Is there anything else we would like to know about it? So like if you say that it is a 0.8 correlation, I may want to know something else about the data, and that is where I will go further with it. The R value is the correlation coefficient, and then we also have a significance value. So in the one that I just talked about in this slide, in over here where it was 0.8, and I could take any value, but you have to, so P is greater than 0.001. We'll talk about this as we go forward, but what you really need to see is the R square. R square is actually called it is the proportion of variability. So when I square the correlation coefficient, it exaggerates the relationships, and it helps you provide a better way of stating your results. So if your correlation coefficient is 0.5 and I square it, it would give me a 0.25 and then multiply by 100, so that is 25%. So I could say that there is 25% of the variance in one variable can be explained in the other variables, which means that they are related by 25%. So think about it, that if it is actually 0.8 and I square it and I get like 64%. So if more than 50% of the variance in one is explained by the variance in other, that means they are pretty strongly correlated to each other. 100% is explained, then that means they are totally, completely related to each other. So this is the square is actually a practical significance. It is the proportion of variability that is there. Let's move forward. Is we have already so those representations were showing you strong negative correlation. This is a strong negative correlation. If you talk about no correlation, here it is no correlation. Positive strong correlation. And then as you can see here, we say it to be a weak negative and a weak positive correlation. Try to figure it out yourself as to which one shows the weak negative correlation and a weak positive correlation. Here is another one of our data sets. So if you look at this data set, you are going to see, first of all, what do you think is the correlation? It is a negative correlation over here, because as the X is increasing, the Y is decreasing. But what is important to notice here is this data set. This data set is completely away from the spread of the other data set, and it is called what is an outlier. If you look at page number 63 of your book, it talks about the outliers. And so look at the expert, that is 3.25, and it says we examined the scatter plots to ensure that the relations were not attributable to one or a few outliers. There is group tendency that is not inflated by the extreme points. So this outlier may contribute towards the statistics or may not contribute towards the statistics, but it is very important to be transparent in a research and show that there is an outlier. You do not want the correlation coefficient to be understated or exaggerated in strength because of the outliers in those two relationships that you have. So that is one of those things that you want to keep in mind when you are doing your data set. So let's go and talk about the different types of correlations that is given in your book. One of the most common correlations that is used is the Pearson product moment correlation. If you do not see a correlation name mentioned, it is always the Pearson correlation that is mentioned. The Pearson correlation is you do not need to know the mathematics behind it, but you can see that it takes into account the standard deviation of the x-axis, the this is like a tongue twister for me, abscissa. Again, I'm so sorry for that tongue twisting. Standard deviation of the ordinate, which is the y-axis. It takes the covariance of both of them. That means how much of the variance of one is relating to the variance of the other, and then it is finding out the formula for the Pearson's correlation coefficient. You are not going to be doing any of the mathematics with it, but it is really important to understand that each of the two variables in this case have to be quantitative. They have to be either interval or ratio, because those are the only ones. They have to be the raw scores. Those are the two important points to keep in mind, is the fact that two variables have to be quantitative and they have to be the raw scores. The symbol for is R. It is also sometimes called just Pearson. So, but if it is not mentioned, it is obviously the Pearson one. The next one is the Spearman's rho, which is represented by RS, or here is the symbol. The difference between this correlation is that it looks at the rank order correlation. So if you have the data set, the raw data set, you are actually giving them a rank. So if you look at the height rank, my 73, the largest rank is 73, so that has got one rank. Then 70 is 2, and then 68 is 3, and then 4 and a 5. And then the weight is also ranked, and then I do the correlation between the ranks, which gives me the Spearman's rho. This is also called the rank order correlation. So every one of them is converted to the ranks. That is where we come up with this. It also provides whether the two variables are correlated or not, and then the resulting. But it depends on the researcher as to what they want and their preference as to how they want to do it. Once again, both variables have to be quantitative, so that means it has to be a raw score, interval, or ratio. The next one is the Kendall's tau, which is very similar to the Spearman's rho. But here, what the Kendall's tau does is, what if there is 3 or 4 people who have the same weight? So that means all of them would have the same tie. So it takes care into account the ties of the several tied data points. This is preferred over Spearman's rho by many statistics people. There is an example given on page number 58 of your book, and your scores are 10, 9, 7, 7, 4, and 3. So if you look at the ranks that are being made, you have a 1, 2, 3.5, 3.5, 5, and a 6. So what it did was, it gave a rank of a 3 and a 4, but then it found the average of those and gave them the same ranks. So this is where the difference is between the Spearman's rho and the Kendall tau. Now, let's look at the other two. So these two are the point biserial and the biserial. So if you look at the point biserial and the biserial correlation, the biggest difference, okay, first let me say that these correlation are between a raw score and a dichotomous data set. When we say dichotomous data set is the fact that they have only two values, like male, female, yes, no. So when I look at point biserial, it is dichotomous, is in true dichotomous. That means gender, male, female. There could only be two. There is no continuum in this. I could also say dead or alive. So that is a continuum. That is true dichotomous. They could be either dead, they could be either alive. You cannot have a person in between. Like, I'm not talking about a coma state, but that coma is alive, right? So dead or alive is true dichotomous. But in biserial, your dichotomous is an artificial dichotomous or forced dichotomy. In that, it means is, let's say, if you want to do a category in pass and fail, that is a dichotomous, right? But a pass and fail depends on what is my cutoff. I can make my cutoff to be 70%. So anything above 70% is pass, anything below 70% is fail. But in another case, it could be 60%. So it is not a natural dichotomy, but it is actually a forced one. It could also depend on, let's say, height. I want to say everybody who is above 5 feet is tall, everybody below 5 feet is short. Or this could be everybody above 6 feet. Or I could talk about anything that is not a true dichotomy is called to be an artificial or forced one. This is what is the biggest difference between the point biserial and the serial correlation. On page 59 and 60 of your book is where they talk about these things, is relationship between the height of the basketball player and whether they score any points. This bivariate relationship is between the two data sets, in which one of them is actually a nominal data set, a dichotomous data set. So that is where the big difference occurs in this, and it is symbolized by R. See, if you can look at it, R is always there. So if you only see an R, that is a Pearson's correlation. But if it has a subscript of the different subscript that we've been seeing is, but if it have a subscript of PB, that is point biserial, and then BIS is biserial. So the last one that we want to talk about is the Kramer's V. The Kramer's V is a unique one in which both variables are a nominal type, in which that means that it just shows us, measures the strength of relationship between the nominal variables. Most researchers do not use this often, but yes, there are researchers that have used this and it is statistically correct. So that is one of those things. So in summary, basically your ordinal scale, you have Spearman's and Kendall's top, but your interval and the ratio scale is your Pearson's product moment correlation. This is the most important one and it's the most commonly used correlation. Best of luck for this assignment. Let me know if you have any questions, guys. Don't forget to post on the course question discussion board.